Okay, so there was we want to do a little op-amp example, so I thought I would do an inverting op-amp for fun. So let's say we have a voltage source here, and we go into a resistor, call it R1, and that goes into the inverting input of an op-amp. And we connect the non-inverting input to ground. And then on the output, we feed back. We'll put a resistor in the feedback path. Put R2 in the feedback path, and we'll connect it to this inverting input. So there's our R2. So we're working with a negative feedback op-amp circuit. We want to know what the output voltage is going to be. Okay? So we can go through and do different loops and all that, but the place to start whenever there's an op-amp is to say, okay, what are the assumptions we're going to make about the op-amp? First of all, we're going to assume that it doesn't draw any current, right? Okay, so we aren't expecting any current to go in through the plus or through here. So no current. I equals 0, I equals 0. We're also going to assume that V plus is approximately equal to V minus. Okay, this, when you have negative feedback, is equivalent to assuming that your open loop gain for your op-amp is very large, okay, like 10 to the 5 or something, like it virtually always is. So what we can do, and this typically greatly simplifies the analysis, what that means is that we can quickly find out the voltage across R1, because if V minus is approximately equal to V plus, and V plus is connected to ground, that means that this voltage, the voltage drop across R1, has to be just Vs, right? If we assume our drops in this direction. So we would say that VR1 is just equal to Vs. Okay? Pretty nice, because this is essentially connected to ground. Great. Now we can look and see, we want to see V out. If we write the loop equation, the KVL equation for this outer loop here, we have Vs minus VR1 minus VR2 minus V out equals 0, or equivalently V out equals Vs minus VR1 minus VR2. So if we knew VR1 and VR2, we would be able to find our output voltage, right? Vs is the input. It's going to be in terms of the input, whatever our final answer is here. So VR1 we already know. So now we just need to figure out what VR2 is going to be. And conveniently, so VR2 has the elemental equation that IR2 R2 multiply to give us VR2. And if we look at KCL at this node here, we see that there's no current being drawn into this inverting input of the amplifier. So all the current that flows through R1 flows through R2, right? In other words, IR2 equals IR1. IR1 from the Ohm's law, elemental equation for R1, is just VR1 over R1. Okay, so plugging this into this and plugging that into that, we get that VR2 is equal to R2 over R1 times VR2. 1. Okay? We plug this, we know VR1, right, from up here. So we'll plug this into each of these. We get Vs minus, VR1 is just Vs, minus R2 over R1, VR1, which is just Vs, right? So the Vs's cancel there, and you're left with negative R2 over R1 Vs. So this method is a little bit hard for our minds sometimes when we're like, okay, I assume these two voltages were the same, and it kind of freaks us out that now this is ground. Allow yourself to do a few of these problems and become more familiar with what happens when you make that assumption. There are several examples in the electronics text in the chapter 4 problems. You can work through them and see. If you want to, I would say I would encourage you to try not making that assumption and instead using the elemental equation that says that V out is equal to a large open loop gain times V plus minus V minus, and go through your analysis and then assume that A is large. Okay? You should get the same result that you get with this method. Okay? All right. That's all for this example.